some examples, right? Basically what I'm doing here is I'm estimating this probability distribution. It's the same thing as a unigram model. What is different in this case, I guess if you're trying to compare it to other cases where you saw unigrams, I am estimating a probability distribution from a 3 or 2 word sample. Right? So I'm not taking a big chunk of text and counting. I'm using that Bayesian approach that we had on the last 2 slides. Right? So here are examples that you would get, right? So if you get something like, well, I don't know, all of these are probably relatively unfamiliar, but if you take, right? So for example, rats in space, right? There was a shuttle mission which sent some rats into space, and they looked at what happened to them, right? So if you take that as your sample text and you use the procedure on the previous slide, you get this as the unigram probability distribution, right? So it has high probabilities for rats and space, as you would expect it, right? It also has high probabilities for a lot of words that you would expect to see in the same documents as rats in space. So these are words that are related to rats in space, right? Shuttle, Columbian, mission, brain, must have been a brain study of some kind. And you can look at other things, right? So Unabomber, well, that's Ted Kaczynski, and there was a big trial, and yes, he was found guilty in the end, right? So, so what is this? This is a technique where if you have a big corpus of unrelated material, or possibly related material, and if you have a sample of words, but this sample is very, very small, but you want to estimate a full unigram distribution, this technique allows you to do that. So estimate a full distribution from a very, very short sample of text. And of course, the way we're going to use it is now we can use it for ranking, right? Because remember, the biggest problem with the probability ranking principle is you don't have any examples of relevant documents, so you can't estimate a distribution that corresponds to the relevant class. The only thing that you have is the query, and this is a method that allows you to estimate that probability distribution based on just the query. It's an estimate, of course, but it's a really good estimate. So let's summarize the steps that we took to get there, right? So that's our probability ranking principle. We want to rank by the posterior probability of relevance. So this was the standard part, right? We take it to this form, and we have to estimate 2 models, the relevance model and the background model. Background model, just approximated by the collection as a whole, by the data set. Relevance model, we said that we're going to approximate it as a conditional probability of a word given the query. And and that is just the ratio of 2 joints. So to compute the joints, we assume that the words are exchangeable, order invariant. And the big thing here is to make sure that you understand that exchangeable and independent are really different things. They're related, but they're different. So that's what the first slide was about. Once you assume exchangeability, you know that this distribution, the joint distribution, is going to have the following form. And it's just up to you how you set the pies, right? And how we set the pies, we just pick the uniform distribution over the points, over the urns that correspond to the documents that we observe in our data, and then each document is just a smoothed relative frequency distribution, right? So that's the set of assumptions. You do that, you end up with a relevance model.